So, what do we got in the way of homework questions here?
Page 476, number 30.
476, number 30. Oh yeah, good. All right, so in general, if I have a problem, so real quick, a little warm-up question to that question. So we'll do that question after this.
Oh.
So again, the one we're looking at is number 30 in section 7.2. So a related question. If I had 11 is 14% of what? Actually, make this a little more interesting. 11 is 1.4% of what? How would you set that up? So 11 is good, equals? So you got to change that percentage into a decimal. Of what? And then you would divide, good, by the 0.014, right? And you get your answer that way. All right, so that's, and then you get x equals whatever the hell that is. Right? Is that cool? So the main problem with this is they give you an ugly percentage number. They give you a percentage number that's a mixed fraction percentage. So a few problems I've graded. This is number 30 again. So 7.2 is 6.25% of what? So the mistake I see people making is they'll say 7.2 is 6.25x. And that is no good. It's the same mistake as saying up here 1.4 here. That's no good either. 1.4% is 0.014 as a real number. Percentages are something we made up so that it would make more sense to us. Really. But math doesn't want to see that crap. Math says, give me the real number. Don't give me the stuff you made up, human. Give me the real number, right? So that's not good. That's 6.25. It should still have a percent symbol there. So there's a little work before you can set the equation up. You have to say, okay, 7.2 is 6.25%. So you haven't started setting the problem up yet. You just translated what it gave you into a better form. Now it's like that one. I mean, here I could have said 1 4/10. So you would have written 1.4, and then you can move the decimal. The problem with this is you can't see the decimal. It's written as a fraction. It's written as a mixed fraction, mixed number. So that's not good. Now I can see the decimal. So how would I write that?
Twice.
So 0.0625x, and then you divide by that. So just don't feel like you've done enough work just because you rewrote 6.25 to be 6.25. That's still a percentage. You haven't moved the decimal place. It's still that percent. So you can't use 6.25 in the equation. You haven't made it into a normal number. It's still a percent. You still have to move the decimal back.
So then you divide the 0.
Yeah, then you divide and you're done. Whatever this comes out to be. So it's like I said, if this problem would have said 11 is 1 4/10% of what, my first problem is really to translate that into a decimal percentage form, because then I can move the decimal around. I haven't made it a true decimal yet. It's just a percentage with a decimal in it. When I do this, that's a real number. That's true decimal form. You guys see the difference there? Just because you did something doesn't mean you did everything. You just did something. The real key from here to equation is going from percent to true decimal. And if you just do this, you haven't done that yet. It's still a percent.
So then when you're dividing to finish solving it, you would take, so it's 7.2 divided by the 0 point, and then would you then move?
Oh yeah, so if you had to do this by hand,
Well, you just finish sorting it out, right? Yeah.
this is not one I'd make you do by hand, but if you had to, you'd have to move this how many times over? 4, yeah? So you have to move this one. 1, 2, 3, 4. Right? And that looks fun. No. I mean, you can still do it. 625 goes into 720. You can still attack it.
So then the answer is just going to be like 7.2 over that. Leave it like
And
that.
well, no, new calculator.
Oh.
Yeah, that's fine. I'm going to obviously make sure you can do this. But once you've shown me you can do this, I'm not going to make you do that everywhere. Right? Calculators do exist for a purpose. We do need to know how to do this on our own, but I'm not going to make you do that in every single problem. Yeah. Okay. Anything else from?
I have a question. If we have like 0.333, like we want to change it into like a fraction, how do we do that?
But it wasn't given to you like this, right?
Yeah, like that.
They didn't say change this into a fraction, no.
And my homework is 33, 1/3%.
Ah, okay, so they didn't give it to you like this.
No.
So they gave it to you like this. So this was the percentage, and then you had to have it as a decimal and a fraction, right? Okay, so to change it into a fraction, what do you have to do from the percentage? So this is, there's a few different ways to do this. As a decimal, what would you do?
Move it over.
Yeah, so right now it's 33.3 repeating, right? So how do you make that from a percentage to a decimal? Move it once, twice. So now it's 0.333. Now it's just 0.3 repeating. And 0.3 repeating is 1/3. In fact, I had to use that fact to get there. Yeah, so that's just 1/3. Right. Another way to look at it, this is, how do you change this into a mixed number? Yeah, so this will be 100 over 3, is that cool? Percent. And another way to think about the percentage symbol is it means division by 100, right? It's dividing by 100. That's why I always move the decimal back when I'm doing this, because this means divide by 100. And when I divide by 100, what does the decimal do? It goes back twice. That's really what I'm doing. So right here I could say this is 100/3. What's the percent symbol mean? Divide by 100. And what happens there? 1/3. Yeah. So you could do that also. We should start picking some of this stuff up. Right now, you should know 0.3 repeating is 1/3. You should just know that. That is a known fact, which is useful. Okay. Anything else from homework stuff?
I have one, number 42 from 7.2.
What percent of 500 is 2? Okay, so how do I set this up? What percent of 500? How do I write that?
X over 100?
Uh,
No.
you could.
Well, that's what I did. I did X
All
over
right.
100.
So we'll do it the more general way. What percent of 500 is 2? Okay. And actually, what's the most basic idea of percentage? They're saying the part that's 2. You got 2 out of 500. They're asking what percent of 500 is 2. 2 out of 500 is what percent? So that's what really matches up on the next step. What am I going to do on the next step? Divide by 500. I'm going to end up with 2 out of 500. That's actually a way I could see the question from the beginning. What the part is 2, the whole is 500. So 2 out of 500. Now the way you're talking about it is there's a lot of different ways that throw 100 into the problem specifically, and that's fine if you already know those. I tend to try to stay away from that because then it's just a form you're memorizing instead of exact translation from English to math, which is the more generally useful thing to know how to do. But here, if you do 2 divided by 500, what do you get? You make it a decimal. Yeah. Another way to do this, watch. If you multiply by 2, don't you get 4 over 1,000? 4 thousandths, tens, hundreds, thousands, 4 thousandths. If you make the bottoms a multiple of 10, all of this stuff becomes a lot easier. Because that's what decimals are, right? And then how do I make that a percentage?
0.4%.
Yeah, 0.4%. I like it. It's a little less than 0.5%. So 2 is a very small part of 500, so that makes sense. It's not even 1% of 500. What would 1% of 500 be? 5. This is a really good ability to have. 1% of 500 is 5. Because 1% is 1 over 100. So you're really just taking 1/100th of 500, which of course is 5. Do you guys see that? So if 1% of 500 is 5, and I'm saying what percent is 2? Well, it's definitely going to be less than 1%. 1% of 500 would be 5, and I've only got freaking 2. So it's going to be less than 1%. In fact, it's going to be less than half of 1%. And it is. It's less than half of a percent. It's 0.4%, a little bit less. So it makes sense. It's really good to be able to do this kind of thing. If I got 1% or 10% of 4,900, who knows what that would be?
490.
Exactly. What is 10%? It's 10 out of 100, so it's actually 1/10 of something. So 1/10 of 4,900 would be 490. Does that make sense? If you're able to figure out 1% of something, 10% of something, and all those are move the decimal place. So 1% of something would move the decimal twice, because it's 1 over 100. It's got 2 zeros. It's going to move the decimal back twice. 10% of something is going to move it back once. And that makes a lot of percentages so much easier to just guesstimate. And most of the time you really just need a decent estimate. All right, so if I had what is 12% of, what you got, Jeff? 2,198. Right, if I had to do that really quickly, I would say, well, that's about 10% of 2,200. 10% of 2,200 is 220, and that's a decent estimate. That's what 10% does, exactly. 10% of something knocks a 0 off of that thing. Right, if you don't quite fully get that, all right, you technically don't need to know that to do these kind of problems, but the more you're able to get something like that, the more you're able to just exist in the real world, because you can just estimate things very quickly. Make sure a store did their math correctly. Never assume they're doing their math correctly, either because they don't know it or because they purposely know it and don't want to do it correctly because they want to get more money from it. Right? So you got to be able to estimate things. Okay. So anything else from homework before we get back into chapter 8? Okay. Who was not here last time needs a handout? Anybody need this handout? Hold on, let me see how I have this left. I think we're good. Yep. Okay. I'm not going to do that one again. You can watch the video. Or if you want to print out of this, you can ask me real nice that I can print one out of this for you in my office. Actually, I cannot. My copier is dead.
Even your slow one?
So that's too bad. That's a printer. So I can't copy this on that bad boy. The other one's a everything. It's a scan and a fax. What's that?
Yes.
Yeah, I can use my home scanner. Yeah, so if somebody emails me and reminds me, I can do that. Sure. You could always watch the video from that day. But we'll do a few review problems. Just make sure everybody's with us.
Do you have another one?
I sort of do. It's got stuff on it. Yeah, you got it. Well, let's do some review problems real quick. And then we'll finish this chapter out. So if I give you... One reason we graph equations is because it's the quickest way to answer the question, what are the answers to this? Because how many answers are there to this? Am I going with that?
Two. Three,
No, it's more than
four.
two. There's always a pair of answers, and that's a point. How many points, how many pairs of answers will actually work in this equation? An infinite number. Every single x value that I pick will have a corresponding y value that goes with it. And how many x values could you come up with? An infinite number, right? In fact, I can get in between 1 and 2, there are an infinite number of numbers to pick. There's 1, there's 1.0000001, there's 1.0000002, there's 1.0, okay. Well, let's not do those. We'll just pick those up on the way. So good ones to plug in there would be some negative numbers, 0, some positive numbers. So go ahead and take a minute and finish that out. I'll do the first one, just in case you weren't here last time and you have no idea what the hell's going on. This kind of problem, all it really boils down to fill out this table is to take the value that I give you and plug it in. I could give you x or y. Whichever one I can give you, you just solve for the other one. So it's just like problems we did way earlier in the semester, where I said let A be 3 and B be 2, and you had to plug them in. So on the first one I say let x equal negative 1. So in place of x, I put a negative 1. So I'm going to get y equals 3 plus 5, I get y equals 8. Which means that that pair of numbers together answer that equation. They are an answer to that. They're a solution to that. So you finished out the other ones. So to get the second y value, so very often we call these guys input, and these guys would be output. It's crazy. Because most equations we can write it so that x is the one that has all the stuff happening to it, and y is just sitting over here like whenever you're done, right? So when we plug a 0 in for x, stuff happens, and then y comes popping out. So that's why we call that the output, and x is the input. It's not always, doesn't have to always be like that, but that's classically the way it is. So here I'm going to put, in place of x, I'm going to put 0. Y equals 5.
No, yeah, never.
So cool. Because the negative 3 times 0 just goes away. So let that part die. And get plus 5. So then another pair of numbers that go together is 0, 5. What do you guys get when you put a 1 in there?
2.
I like it. Negative 3 plus 5 is 2. So now those numbers go together. And then when you plug a 2 in there,
-4.
yeah, you get negative 6 plus 5, negative 1. I like it. So those numbers go together as a point. And you just make it a visual representation of what's going on. And it seems like a very simple, if you think about it, it's the most simplistic way we could possibly come up with is, we already have an x-axis, let's just slap a y-axis going the other way. X controls left and right, y controls up and down. And then in the future, if you get far enough in mathematics, you'll have another one coming out the board. That would be the z-axis controlling out and in, right? Because in the real world, I have a point in three-dimensional space, and I want to know how much do I go over, up to get there. But thankfully, in this class, we'll just stick to 2D, right? No classes, no glasses required to see these problems. No headaches. So if I want to plot this graph, so this is another skill, a basic skill that you have to be able to do this kind of problem, is how do you find points on this coordinate system? All right, that's always exciting. Watch me do this. How about them Chargers? Huh? The Dolphins almost did the same thing. All right. So negative 1, 8 would be actually, if I try to go a little further up, there's 6, 7, 8. So negative 1 would tell me to go where? I kind of gave it away there, but oh well. Yeah, negative 1 would be, x is the first guy, so that's left and right. So x says go back 1, and then up 8, and that's where I put a point. You don't put a point there. You put a point after you've done what both of these say to do. Right, so it's the same thing as saying I live a block back and 8 blocks up. That's where my house is. And so a bike over there and bike over there. Right? 0, 5. So how far do I go left to right? Nowhere. I go nowhere on the x-axis, but in the y direction I go. Cool. 1, 2. Yeah, 1 to the right, up 2. And then 2, negative 1. Right 2. Down 1. I love it. Now notice something. Every time my x goes up by 1, every time I take one step in the x direction, how much do I have to go in the y direction? How much do I go from 5 to 2? I go down 3. Over 1, down 3. Over 1, down 3. Over 1, down 3. Some of you guys might know that that's leading to the idea of slope. The slope of the line. This is a negative slope. It's a straight line. So the minute, if I change that rule, over 1, down 3, over 1, down 3, if I suddenly went over 1, down 4, it's not straight anymore. It had a curve to get there. You see that? If it's a straight line, it's got to have that same rule every time. So I think about like a hiking through the forest, and it's a straight path. If you go off the path, you just got to know the rule to get back to the path. Right? So the slope tells me how to get back to the path. So here's the safe path. Stay on the road. Don't go on the moors. So if you go over 1, down 3, over 1, down 3, so forth. And look at the equation. Interesting. So if that would have been negative 2, my rule would have been over 1, down 2. Over 1, down 2. That's kind of cool. We did one like that last time with the negative 2 there. Okay, so that's really capturing a lot. They capture stuff from 8.3 and 8.4. 8.3 just focuses on the points and the graphing. 8.4 focuses on the equations and how they lead to points. Here's one kind of problem we haven't done yet. Check to see if the given point is a solution to which guy, Jeff? Sure. All right, so let's see what you guys think about this. So, let's make this interesting. So how do you think you do that kind of problem? How do I check so I'm given, in each section I'm given a point. How do I check to see if that point is a solution to that equation? How do I check any solution? Plug it in. But you have to be careful now. Where would I put 1? I love it, because the first guy's X, second guy's Y. So to check this, I would say, just like I always do, how do I check any equation solution? I plug it back in. So 4 times 1 minus negative 2. So you gotta be careful. There's a minus negative 2. So I get 4 plus 2 is 6, not 7. So this, not a solution. So real quick, just to kind of tie that with this, do you see how there's a lot more points than what we did here? Every single point that my line goes through, all these weird points, like 0.1, comma, 4.2, or something or other. You with me? Whatever that point is, that's going to be a solution to the equation. Every single point that this line goes through. So what is that point all about? That point would not work in that equation. That's the connection. So a line goes through all the answers to the given equation. You guys with me? I know I keep saying the same thing in different ways, but it's really trying to hammer home what the hell this is all about. So that's why this is a visual answer to the question, what are all the answers? Well, there they are. What about 2-1? So try the other 2 there on your own. That's crazy. So on part B, you have to check it. You would say 4 times 2. Next is 2. Minus 1 is Y. And that is 8 minus 1, which is 7. Check. So 2-1. 2-1 does what? It's a solution to that equation, and visually, that point would be on the line this makes. That point would be on this line. This point would be off the line. You with me? And again, I keep saying the same thing over and over again. That's the way to get it. And finally, this dude, it looks disgusting, but it becomes pretty easy once you plug it in there. So 4 times 7/4 minus 0. Well, 4 times 7/4 is 7. Check. So this point would lie on that line. That point is the solution to that equation.
What about the other one in the middle?
Yeah, it's just what circle, check. Because it equals 7. When you plug it in, it makes it true. Therefore, it is a solution. Okay. So let me show you something kind of nifty. This is way yes.
Now, 1 and negative 2 doesn't work together, but that doesn't mean we don't have another 2 for 1, right? 1 will work with something else.
Exactly. I like it. So these are very specific. 1, negative 2 does not work, but 1 comma something else might. In fact, we could figure out what that is, couldn't we? Yeah, we could. So if I want to know, okay, 1, negative 2 didn't work, but 1 what works? So how would I figure that out?
Plug it in.
Yeah, plug it. It's crazy. 4 times 1 minus, I don't know, so that's still y, is 7.
5 minus 1.
So minus 4, negative y equals 3. So then y equals negative. So 1, negative 2 is not quite right. 1, negative 3 would be there. It would be on the line. I like it. Oh, yeah, all kinds of weirdness going on here. So if you obviously do not need a graphic calculator for this course, but if you have one, I want to show you some stuff. If you feel at all like playing around with this thing, if you hit that y equals button, that brings this up. So for example, that negative 3x plus 5. You put negative 3x plus 5 in a graph. Right, there it is. It is correct. But then you can put stuff in that's not in the not in this course really, but we've talked about exponents, right? So if you put in there x squared, y equals x squared, it makes that shape. And think about it, it makes sense. What's 2 squared? What's 2 squared? 2 squared is 4. What's negative 2 squared? Negative 2 squared is also 4, right? Because negative 9 is negative 5. So 2 goes to 4 and negative 2 goes to 4. It's symmetric. Right? Woogie, woogie, woogie. So I say that. I say that in my head. And then you can get really, really cool, funky things that you're not even sure what the hell they are. Come on. Right? That's the snake graph. And then you can get, now just to truly freak you out. Go with me for a second.
Can you tell us in English what you're doing?
That's cool. Sorry. Just trying to show you the possibilities of what's going on here. So let me make this a little bit bigger. So again, like I just said, this is well beyond this, but I just want to show you the idea of graphing. This is the beginning of it, but it just doesn't end after you begin to learn it. Because every time you hit a new function, you want to know what it looks like, and then you can develop. Why does it have to be x, y? Why couldn't it be something else? Why couldn't there be other ways to represent that? So, let me make this a little bit bigger so we can see what's going on. Crack. No.
Next class.
That's cool.
Football.
Yeah.
Yeah, football.
Make a turkey.
That's a chick.
It's a turkey in a blender right there.
But this is neat, though. Do you see what I just plugged in? Now you don't really, you obviously don't understand what's going on here for several reasons. There's like 2 parts to it. The COS and the SIN stuff is just a function that you don't know yet. It doesn't mean a damn thing about anything. Just you've never worked with it, so how would you know it? But basically, it's a function that makes this shape. And you see, like on an oscilloscope, or if anybody works with sound in any way, any musicians or anything, when you pluck a string, it makes that kind of vibration. You see it, right? That's the function, this mathematical function that models that vibration. That's all that sine, that's all the SIN and the COS are. So somehow this merges them together, and we may try to make it so you can see a little better. And has anybody ever played with that thing called spirograph? Anybody ever heard of that? Some of my older students maybe?
Looks like an owl. That's just kidding.
Yeah, little different gears that you would put your pencil in, and it would go around and make these cool little things. Yeah, back in the day before there was the internet, for example. Even before Xboxes. It's crazy.
Wow.
Way back in the dark ages. Anyway, so my only purpose for showing this is not to say this is going to be the final. You're not obviously at all responsible for this. But just to show you where something like understanding how to graph could eventually lead. And there's a reason for knowing how to do this stuff. This could model something going back and forth. Who knows? This could be an atom bouncing off the wall somewhere. Who knows what this could be? You want to model what it's doing so you know where the hell it is. Okay. So enough of that there. So if you do happen to have a graphing calculator, I know that you're not all like me. When I was a little kid, my favorite toy was a calculator. But yeah, when they come over, they're like, wow. It's kind of a major admission. Not quite. I'd say it was on par with Legos and stuff, but it was up there. Calculators were up there. You should still feel comfortable and not feel at all worried about yourself that you're becoming at all like me if you just play with the calculator a little bit and just see what things look like and just plug stuff in. Try x cubed. Try x to the 1/3. Try weird shit and just see what it looks like. Why not? If you have one. If you don't have one, I'm not saying go get one. They're freaking expensive, right? Okay. So let me make sure if there's any other little things here. Cool. Okay. There's one last thing here to talk about in chapter 8. And I might throw in one other thing too. Yes. Okay, yeah. So, basically, if I have an equation like this, well, let me not pick you up. In general, if I have an equation like that, I can plug values in for x and y, I can get values out, I can make little points, I can plot them. This is going to be a straight line. Can anybody tell me why for sure it's going to be straight, not curvy?
Because we don't have square.
I don't have any power except first power, right? There's an understood first power on those two variables, right? There's always going to be a linear function. So if both variables are in the equation, it's always going to be at some diagonal. It's always going to be diagonal. But what about a function? What would be the function that would lead to a picture that looks like this? That's my line. What's the defining quality of that line? Every point on that line has something in common. It's kind of stuck somewhere. What would you say is the defining thing about that line? What's always true? Where is it? How would you just describe it to somebody? Yeah, what's true about the x value for every point? Think about it. What point is this? A point has two parts to it, right? It's got an x part, comma, y part. So what point is this? 2, 1. What point is this? 2, 2. What point is this? 2, -2. So what's true about every single point on that line? X is 2. So guess what? That's the equation of a line. That's the equation. X is 2. Does this line care what y is? What could y be? Anything. So that's why it doesn't show up in the equation. Think about it. If it shows up in the equation, I can control it. I can make it something, and the other dude will make that other guy come out to be something that can kind of play off each other. They're controlled. Y is not in this equation. It can do whatever the hell it wants to. Can it be 80 billion? Yeah, that sucker keeps going. You guys kind of with me? But what's x got to do? X has got to be 2. So really, when I see an equation like that, that tells me every point has to look like this. And what does this have to be? Anything. As long as x is 2, the equation is happy. So that's why it ends up being a straight up and down line. So what would the equation for this be? X is negative 3. Because again, that's the defining quality of that line. X is always negative 3. Does it move left or right? No, so x has to be the same. It only moves up and down, which means y can do whatever the hell it wants to. How do you guys feel about that? Yes, sir.
Is y 0? I mean, that center piece right there, is that 0?
Right here?
Yeah, no. Over one.
Here.
One in the middle. Yeah, is that?
Yeah, that's the point. What point is right in the middle of everything? 0, 0. It's not over and not up or down. Yeah, so that's...
Okay, I see what you're doing now.
All right, cool. Maybe. So what do you think about a line that looks like that?
Why is
Y is 3. I'm not allowed to move up or down. I've got to stay at 3. So what variable is up and down? Y. So I have to control. I have to say, Y, you got to stay at 3. X, you go crazy. I don't care. You're going to be everything. Every X value is represented. But only Y equals 3 is there. So that's why that's the equation of the line. If you have an equation like X plus Y equals 7, that means when X changes, Y also changes, right? They play off each other. That's always going to be diagonal then. Both the left and right and the up and down are changing. So I'm going to get some kind of diagonal line out of that. These are extreme cases. X is missing, Y is missing. They don't play off each other. That's why it's not going to be diagonal. Only one variable is changing. In this case, X is allowed to go all over the place. It moves left and right. In this case, Y can do whatever the hell it wants to. So it's going to only go up and down. So remember, those are special cases. Don't ever try to force them to act the same way these do. Because they won't. They're special cases. X equals Y equals. And a really cool way to remember this, well, let's see. This is not a really good way. It's actually backwards. The unfortunate thing is the X equals equation. And I like the fact you were saying parallel earlier. I think it was you saying parallel. It's parallel to the Y-axis. So it's not a good way to remember it, because the X equals equation is parallel to the Y-axis. Damn. But the X equals equation goes through the X-axis, right? Whereas the Y equals equation, in general, won't. Okay, maybe. All right, you guys love that part. Okay. So that's that. Those two special cases. X equals something will always be vertical line, and Y equals something will always be horizontal line. If you have both variables in your equation, it's going to be some kind of diagonal. Okay. All right. The other thing is, and I think this is more than what the book says, but when I have a line that's diagonal like that, I have two very special points. I have this point there and that point there. Now, crazy enough, why do I pick those 2 points as being the two special points? They're touching the axes. I love it. So this one's touching the Y-axis, and this one's touching the X-axis. So math people, being the remarkably clever people we are, we said that one intercepts the Y, so we're going to call it the Y-intercept. This is called the Y-intercept. This one's called the X-intercept. Crazy. So any line you can think of. So if I draw another one, just one more here before I get too full up. There's the Y-intercept. There's the X-intercept. You with me? So what must always be true for any X-intercept? See how the x, I can hit the x-axis anywhere. But what's the y going to be for any x-intercept? Like, for example, what's this point here? What point is that? 3, 0, because it didn't go up or down at all. What point is this one? Yeah, -1, 0. I didn't go up or down at all. It's on the x-axis. So y is always going to be 0 for an x-intercept. And I'll bet you for a y-intercept, I don't move left or right at all, so the x is always going to be 0 for the y-intercept. All right, so for a y-intercept, x is 0. For an x-intercept, y is 0. So watch this. That kind of leads to a really cool way to graph lines. If I had this equation, this kind of leads to a way to find two special points.
Is that the y-intercept and then
X-intercept. Yeah, y-intercept, x is 0. X-intercept, y is 0. So watch this. To find the x-intercept. To find the x-intercept. What's true at the x-intercept? Y is 0. So to find it, I force y to be 0.
Yes.
So if I set y equal to 0, what do I get from my equation? X is 5. So what point is that? Careful. Y is 0. So how do I find the y-intercept?
Zeros.
Set x to 0. That's cool. To find one intercept, you set the other letter to 0. So to find the y-intercept that set x to 0, what would I get? So somebody was just a little ahead of themselves?
1.
Yeah. Divide by 5. Y is 1. So the point is 0, 1. So if I graph those 2 points, that's all I really need for a straight line, is 2 points. So graph those 2 points, 5, 0, and 0, 1. There's the line there. And the reason those are special points is because very often we look at this as time. In fact, most graphs you see in the paper are like in the year 2007, 2008, 2009, they show us unemployment rate or something, right? And they graph the unemployment rate. So this would be somehow at time equal to 0. At the beginning, whatever I'm considering to be the beginning, that's where it was. So that would be like the initial place where I was, the first place I was. And then I see, here's our profit. And then, over the last 5 years, oh shit. Right? Our profit has been steadily decreasing. And then I want to know, well, here, that would be where I'm just breaking even, if I'm talking about profit. Right? I'm at 0 profit. My cost equals my revenue. I'm not making any money. You guys kind of with me? So that's why that's the other point. That's where my output is 0. So this would be something like break-even point. If this represented a rocket being fired, this is where it leaves the plane, and this is where it hits the ground.
Blanks.
You with me? So that would be, we often consider the x-axis the ground. Because we actually call these x-intercepts, we also call them roots.
The sky and the ground.
Because right at the ground is where the roots start, so we call them roots of the function. All right, put me there. You guys are loving this stuff, I can tell. All right, so I just want to do a little preview of chapter 9, and then we're going to leave plenty early. Right, it's a little compromise for Thanksgiving. I want to do one thing. I'll talk about a couple things in general, but then do one thing you guys have probably never seen. So the only thing we're doing with geometry really is going to focus on area and maybe some volumes, right? So we're not going to do any side-angle side proofs. We're not going to do any transversals of parallel lines. We're not going to do any of that stuff. We're just going to focus on areas and volumes. Because in algebra, you're going to have word problems involving areas, perimeters, stuff like that. So you got to do a little review, make sure you know them.
That's 90.
Yeah, Math 90, Math 103, you can have word problems involving some geometry. Yeah. Just to let you know what's ahead.
For next semester.
So what's the relationship between a square and a rectangle?
They both have the number of sides.
Number of
sides.
What's the same thing? They both have 4 sides, but much more specifically, they actually can't be all like that. They have to be perfectly straight. They have to be at what angle?
Right?
Right angles. I love it. Because the minute you move it, it's like a rhombus or a parallelogram, right? You get all kind of neat stuff, right? Rhombus sounds like some kind of rutabaga vegetable. But a square and a rectangle in general. Let's go read. A square would have what defining quality about all the sides? They're all the same size. So if this was X, this has got to be X. You're talking about rectangle there. So what's the perimeter? Careful. Yeah, perimeters, add them all up, so it'd be X, 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 it'd be 4X. And what would the area be?
X by X.
X times X, which is X squared. I like it. But you really don't need specific equations for a square, because the relationship between these two is a square is a specific kind of rectangle. It's the rectangle that happens to have the same side lengths with me. So everything that's true about rectangles must also be true about squares. So here I would call this maybe width and length. So what would the perimeter and the area be? What's the perimeter? Yeah, because you got to add all the way around, so you get a couple W's and a couple L's. And what's the area going to be?
2 times.
Careful.
L times
It's just length times width.
All together?
Just length times width. That's where this came from, isn't it? Area for a rectangle in general is length times width. Here it just happened to have the same length and width, so I was able to make it X squared. I can do that. Here I can't do shit with that. L times W. They're not the same. I can't consolidate. But they're really the same exact equations. Okay, nothing exciting there yet. What about a triangle? So triangle is really, one way I can construct a triangle is to take a rectangle, cut it in half, right? So if I call this, instead of W, I'm going to call this the base. And instead of L, I'm going to call this the height. What would the area be for that rectangle? I'm with you where you're going. But what would the area be for that rectangle? It would just be base times height, right? Just like it was width times length. You with me? And of course, somebody's there for me already. The minute I cut it in half, it's going to have to be half of that. So some of you guys might know the triangle formula is 1/2 base times height. That's why. It's just half of an associated rectangle. I would know so far, so that's nothing amazing. Most of you guys should probably know that already. There's no real perimeter formula. In fact, I wish none of you knew this, but some of you already did, so I might as well put it up there. Perimeter in general is just you add all the sides. And if I don't know the side, for this triangle specifically, what could I do?
The hypotenuse.
It's the hypotenuse, so I could use, what could I use to figure it out? A squared plus B squared equals C squared, whatever you're going to call it. You with me? So if I needed to know, let me know what. So here's a possible problem you could see for me. Hint on a test. I've been known to like to give this problem. I'm going to ask you what the perimeter is for this. Let me make it not too evil. Oh, what you got, Jeff? I don't know. I think that'll work. Let's just make one that I know will work. Okay, there you go. So if I want to know what the perimeter is of that triangle, I can't answer that because I don't know this last length. Because the idea of perimeter is just to add up all the sides, right? All the outside sides. You with me? Yeah, so how would the formula look then? Yeah, so 5 squared plus 12 squared, c squared, x squared. It doesn't matter, yeah. You're good. Good. 25 is 144. 169 is c squared. 13, I love it. So this would be 13. So then the perimeter would be what? 30. 30 whatever. So I would give it feet maybe, so it would be 30 feet. You guys kind of with me? So I can certainly use, you all know the Pythagorean theorem, you've been tested on it, so you better continue to know it. Just because those tests are done, the final's coming, and the final's going to be everything. Right? And of course the next class is going to assume that you know everything from this and go from there. So don't forget, I can use anything we've learned in a problem that deals with new stuff now. So this would be a perimeter of a triangle, which is sort of new, but you'd have to use Pythagorean theorem to figure out the last side, and that's considered now old. It's the last test. What would the area of that be, sir?
What's the theory's name?
Oh, this is the Pythagorean theorem. After Pythagoras. Old Greek dude. That's my 12th puberty. So, what would the area of that triangle be?
5 times 12.
Almost.
Half.
Yeah, it's 1/2. The base times the height. So it's 1/2 the base times the height. 1/2 of 12 is 6 times 5. 30. What units would there be? It's feet, but it's not feet. Feet squared. I like it, so square feet. Why? Because you don't have to do this, please, dear God. But if you brought the units along, foot times foot is feet squared. That's why it is. So if I had volume, it would involve all 3 dimensions getting multiplied. That's why volume would be cubic feet, feet cubed. That's the only reason the units are different for the different dimensions. Okay, last thing for today. There's actually other shapes, but we'll do the other shapes next time. I want to do this one shape today, and that is a circle. Now the weird thing about a circle is that if you take the diameter and you take, what do we call it? We don't call it perimeter. Yeah, so all the way around is called the circumference. It's really just perimeter, but it's a circle, so it gets its own special name. How many sides does it have? Either none or infinitely many, depends on how you want to look at it. But we'll say it has no sides to it. There's no points to it. Like a rectangle has 4 points, 4 vertices. So it gets its own special name for its perimeter. But the really weird thing is, no matter how small you make a circle, or how big, if you cut the earth in half and you look at the rough circle it makes, if you took the circumference divided by the diameter, right? One way you can do this is you can put a piece of string around something like the base of a, well, none of my waste baskets are circular. Too bad for me. Put a string around something that's circular, and then if I lay it out and measure it with a meter stick, that would be measuring the what? Circumference, right? I just kind of took it and made it straight. So I would get the circumference, and then while it's a circle, I measure across the middle, that would be the diameter. And if I divide those two numbers, I don't care how small my circle was, or take the sun and cut that bad boy in half somehow, right? And get that circle, I don't know how big it is, it always comes out to be the same number, which is pi. And civilizations have known about this. The Greeks, the Egyptians, all these people, they had different estimations for what this was. They didn't have computers. They didn't know it was 3.141596, blah, 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 blah. They didn't know all that. We know it now because a computer could just crunch it out. But they had, like, one approximation was, it was about 22 divided by 7. What is 22 divided by 7? Somebody help me out.
Something like
roughly? 2a, blah, blah, blah. That's pretty damn close, right? And then there were other approximations, and mathematicians kept trying to make it better and better. And now, of course, we cheat all the time because we just say, computer, do that. And it does it, you know. But these poor people, they sit there and do it by hand. It's crazy. But you get a rough approximation if you do this. So that's where pi came from. People got freaked out. They were like, that tiny circle, if I divide those two things, it's the same as some giant circles. It always comes out to the same number, and they thought it was holy. They thought it was a gift from God. So they gave it its own symbol. They said that's pi. So that's where that symbol comes from. So that's where we get their circumference formula, is if I multiply d, I get c equals pi d. That's the formula for the circumference of a circle. So that's d. What would just halfway out be? What's that?
Radius.
Radius. Good. So how does the radius relate to the diameter?
half.
Good. The radius is half, so the diameter is twice the radius. Now, all this stuff you should have probably at some point seen before. This shouldn't be too major of a thing. So another way I could write this, see, if you don't know the diameter but you know the radius and you just don't feel like doubling it, another formula for this would be diameter is 2r, so this would be 2 pi r, because 2r is the diameter. Those are both the same equation. Right, just replace d with 2r, because that's what it is. The diameter is twice the radius. So both of those equations work. You definitely should have seen at least one of those, hopefully somewhere in your past. Or geometries in your future. Maybe you escaped without taking geometry. Now here's the part that you've never seen before, probably. And someday I keep saying this, and I don't do it, so I probably won't. But I keep saying someday I'll actually bring construction paper and actually cut it. But I think that would be really exciting, watching me cut construction paper. But and you're all like, what the hell's the guy doing? If I want to know the area of a circle, what I want to do, anytime I want to find the area of a shape that I don't know the area for, I try to rearrange it into a shape I know. You kind of with me? So for example, if I want to know the area of a house shape, there's no house shape area formula out there. You can Google it. It won't show up. But I can cut this into a triangle and a square or a rectangle, and I can find the areas and then add them together, right? So I can try to rearrange or re-look at my shape and shapes that I already know. So here's the kick-ass thing. I'm going to turn this circle into a rectangle, because then the rectangle I know the area for, right? I'm not going to turn it into a rectangle by erasing it and drawing it again. I'm going to actually do something kind of nifty. Now if I cut right down the center, right, so cut that so it opens like Stan's little brother. Like, that's I can't. If you don't watch South Park, you didn't get the reference. If I cut out from the center, but I don't cut all the way out, so I just cut out and then I stop short of the edge. You guys still kind of with me? Just cut out, but don't cut all the way through. Just cut right to the edge. All these little teeth. Can you imagine now I could pick it up and open it? I could pick it up and open it. So then it would look like this. Roughly, right? So just open it up. Now, real quick, how far is this whole thing? What's the circumference? 2 pi r, are you with me? That's 2 pi r. So, how far is just from here to there? How far is that? The whole way is 2 pi r. Halfway is 1 pi r. I love it. So this is pi r. And since I did this, like that, and here's the little points, I just open it up and put it there. How long is this? Pi r. All right, let me let you absorb. The book might, I think this book actually might do this. Yeah, it does. Cool. It's like the first book I've ever seen actually do this. Now do the same exact thing with the bottom. Open it up and just push it in like this. You guys semi with me? So just put it in like teeth. So cut it, and open it, and then shove it in there. Now, how long is each of these teeth? How long is this? What is this? What is that from the center out? What is that? Radius, 11. That's R. So it's R. So this is a rectangle, roughly. It's a little bit slanted, but if I cut my teeth smaller and smaller, it gets more straight and straight. It's a rectangle with, this side is R, this side is pi R. What's the area of that rectangle going to be? R times pi R, which is pi R squared. I don't know if that sounds familiar to anybody. So it's kind of cool. So we cut that circular shape up into a rectangle, pi R squared. You know, and the old joke is pi R not square, pi R round. But pi R squared, that's the formula for it. That's why, because we rearranged it into a shape that we knew. So now you have to know circumference, 2 pi R, or pi d, and the area, pi R squared. So let's do one concrete example, and then we'll call it Thanksgiving cup. Thanksgiving cup? I'll get used to that word. So if I had a circle, let's say the radius is 12 meters. Big ass circle, right? This is one of those irrigation things, farming, that you see when you fly in a plane over and you look down, there's these big circles on the ground. You ever seen those? Have you ever fly before? So, 2 questions. What's the circumference and what's the area? So what formula can you use? What is that 12 that I've given you? What is that?
That's radius.
Radius. So I know the radius is 12. Yep, so the circumference is 2 pi r. So it's 2 pi times 12. So you get 24 pi. And you should see, does everybody, if you have a calculator, make sure you can find, if you have a square root button, there's a good chance you have a pi button on your calculator. If you have a very basic one, probably don't have a pi button on your calculator.
So you don't have no pies.
No pies for you. At least no math pies. Holy crap, this thing's got everything. There it is. Right down there. See that right there? No, above it, in yellow. So you have to do shift to get there. Where's your on button? There it is. Hit shift. Now let go of it. Let go. There you go. You can hit. No, below. There. See, because it's above. There's pi. Hit equals. See what it says. It's probably just going to say pi because you got that weird. Now hit this guy. There you go. See? You guys have, everybody find your pie? Does everybody have a pie?
Yeah, about 2 minutes.
Look under your chair. There's a pie for you and a pie for you. And I'm no. It's been there for a week. Oh, man. If you don't have one, the other class must have found. So if you do 24 pi, if you found your pi button, try to do 24 times pi button. No. Do 24 times pi. Yeah.
3.45.
Do 24
Times
times pi.
75.
75.86.
75.36
36 something.
blah 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 blah. All right.
Just use the number.
Yeah, so you type 24
I did 24
times pi. I love it. And now you remember you always have to do that.
Oh.
Yeah. So we figured that out about your calculator. What would the units be? Circumference. It's not area. Stop. Meters. Right? Circumference is just a length. It's only going to be meters, not square meters. Area is going to be square meters. Area is where I try to cover this thing. What would the area be of this? How do I find the area? Pi r squared. So pi times 12 squared. 12 squared is 144. So you do 144 pi and you get something.
4, 5, 2.
Numbers.
What?
4, 5, 2. 0.16.
Point 16?
Yes.
Yeah, that's what I
Blah, blah, blah.
Sounds like
Square meters. 11. I like that. I've got that too. Don't have a calculator.
I have my phone calculator. Yeah, everything.
Oh, yeah, we can do
All right. So that's plenty for now. We'll finish up chapter 9 on Tuesday. Next Tuesday, I've got the, well, let's see. What's going on? So next week, I've only been thinking about Thanksgiving for a while. So next week is the last week of class, I think, if I remember correctly.
Yeah,
Yeah.
we're not going to have the final exam. Right?
So Tuesday there'll be a. What are you talking about? Not next week, unless you want it next week.
Give it to him.
So next week I'll have the practice final and the answer key. There was an email sent out. Somebody asked me about it. That's in addition to. So when I was the math study center coordinator, I would send it to the instructors too to know what was being sent out. I never get anything anymore, so I don't know what he said. But it's in addition to our own review, so that you should have gotten in your email something from Sean Hicks.
Yes.
He's the Math Study Center coordinator. In fact, there's a posting outside. There's Math 88 review sessions.
I thought it was spam.
That is in addition to what we're going to do in class. Okay? That does not replace what we're going to do in class.
Would you recommend we do that, or?
If you got time, why not?